So we're looking at page 24 in the packet, still Unit 2. Sample space size. The idea behind this is that we should be able to figure out the total number of elements in a sample space without actually having to list out the whole thing. But in order to do that, we want to investigate and see if we can develop a rule that we can apply in all cases, or at least many cases. So flipping a coin, for example, we know that one flip gives 2 outcomes, 2 flips gives 4 outcomes, 3 gives 8. That's all on page 22. Complete the table below. Well, okay, so I got that. Number of outcomes, 2, 4, 8. It looks like the relationship here is that we're multiplying by 2. So logically, to overuse a term, the next one would be 16, or at least it follows that the next one would be 16 if we're doubling. All right, but we can actually determine what the value would be of the number of outcomes based off of the number of outcomes for a single trial, which would be 2. If I flip a coin, there's 2 possible outcomes, and the number of trials. So instead of looking at it in this regard, which is still correct, I could look at that just at this 2 and say, how do I get to the number 2? Well, I take 2 and raise it to the first power. How do I get to the number 4? I take 2 and raise it to the second power. 2 and raise it to the third power. 2 and raise it to the fourth power. And hopefully you see the consistency here between the power and the number of flips. In which case, it follows that the last entry, if you flipped it any number of times that we'll call n, the number of outcomes will be 2 to the nth. All right. Same thing with rolling a die. If I roll a die once, 6 outcomes. Twice, 36. 6 times 6 gives you 36. Times another 6 will give you 216. Times another 6 would give you, 1296. I don't know. Let me take a look. I've done this enough that I should know it. Yeah, apparently I did. I just wasn't confident enough. So 6 can be thought of as 6 to the first power. 36 would be 6 to the second. 216 is 6 to the third. 1296 would be 6 to the fourth. And so we can conclude that if we roll a die n times, so any number of times that we'll call n, that it would be 6 to the nth power. All right, so the base of the exponential seems to be whatever the number of outcomes are for a single trial. I stumbled over that word there for a second. So number of outcomes for a single trial and then we take that and we raise it to the number of trials. I was going to just write n, but I might as well just write it out. Number of trials. All right. Now this is going to work in many cases, but not all cases. That's one of the challenges about probability. You know, there isn't a catch-all that's going to work every time. Otherwise, uncertainty would be kind of certain. Right? So we need to investigate a variety of different circumstances so that we can kind of pick and choose our battles. Anyway, we talked about Venn diagrams. Now we're going to kind of get to the idea of, right, how do we combine basic concepts of probability and the logic that we talked about. So the addition rule is one of the first steps in that direction. I call it the rule of or, and I don't think I'm the only one. It's one of those key words. If you see or in a problem, or the word or is implied, and it's almost certainly an addition rule question. All right. So this refers to any instance in which you're dealing with the union of two sets. All right. So this is set A, and this is set B. everything contained in the marriage of sets A and B would be part of this. Now, sometimes we could just reason out what the probabilities would be just based off of that general understanding. But in a lot of cases, there's some computation involved that we need to account for. So that's coming right up on the next page.